Hello, my name is James Smith. I am a machine learning PhD student at the Georgia Institute of Technology. I'm excited to highlight our group's ICCV 2021 work, Always Be Dreaming, a New Approach for Data-Free Class-Incremental Learning. Our work falls under the continual learning paradigm. As visualized on the right, typical learning with neural networks involves offline training with shuffled data. That is, the distribution of object classes satisfy IID assumptions. In continual learning, tasks are instead encountered sequentially. Shown on the right, we see that classes appear in a single task and only in that task. We encounter the catastrophic forgetting problem, where we overwrite information from past tasks when learning a new task. Continual learning asks, how do we acquire new information without encountering catastrophic forgetting? A classic way to mitigate forgetting in continual learning is through internal replay. As shown on the left, a continual learning agent has a data storage. As the agent moves to future tasks, it mixes in data from the storage with data from the new task. This method, also known as rehearsal, works well for continual learning but has some concerns. First, this method requires substantial memory budget. Second, some data cannot be stored due to privacy concerns. Prior work has instead looked at dreaming synthetic images from a trained classification model as an alternative to storing data. The high-level overview for dreaming or inverting an image from a trained classifier is to set up an optimization problem which tries to uncover the data that the trained model was originally trained on. In our work, we analyze the finding that these dreamed images fail for class-incremental continual learning. This is the main problem addressed in our work. So what happens when we use streamed data for continual learning? On the right, we show a t-SNE visualization of the embedding space for a continual learning agent. The red vertical lines represent real data from the first continual learning task. This is the data we want to classify and has not been seen by the learner since training task 1. The blue horizontal lines represent synthetic data which we dreamed from our first task. This is our replay data when training task 2. The green X's represent real holdout data from the second and most recent task. We have just trained on this data distribution jointly with the synthetic data. We see that real data from the first task is close in the embedding space to the real data from the second task. This is a problem. This data should actually be close to the synthetic data from the first task. This indicates we have a bias in the feature space. Specifically, when training a model on real data from task 2 and synthetic data from task 1, the feature embedding is prioritizing domain content over semantic content. Thus, when evaluated on the real task 1 data, our model falsely predicts class labels from the most recent task, task 2. This bias is the problem we want to prevent in our work. Using these intuitions motivated by our analysis, we present our approach, Always Be Dreaming. On the left, we see that we have synthetic data from our past task and real data from our current task. Both of these batches are fed through our current model being learned, the green model, and a frozen copy of our model from the end of the last task, the blue model. This blue model is used for distilling past task knowledge into our new model. Key to our work is that we avoid the bias problem by learning new features with a local cross-entropy loss calculated only over the current task classification heads. In order to preserve knowledge from past tasks, we add an importance-weighted feature distillation loss, which distills important features learned in the past task into our current model. Finally, to balance the classification heads of the current and past tasks, we include a fine-tuning loss which only updates the classification heads. We see in our updated t-SNE visualization that an ideal embedding space has been learned. Specifically, real task 1 data is clustered with the synthetic task 1 data, while real task 2 data is clustered in separate regions. We found that our approach is state-of-the-art compared to methods which do not store a core set of real images for replay. We even found that our method could outperform methods which do store a coreset of real images for replay. For more details on our method and full classification results, visit our paper or our poster session. Thank you for listening.